I'm glad to introduce this very young researcher, Mr. Kirk J. Taray. Kirk earned his bachelor's degree in biology from the University of the Philippines, Los Baños. He took wildlife biology as a major and focused his undergraduate thesis on bats. In his thesis, he described the echolocation call, determined the emergence patterns, and identified the diet composition of cave-dwelling insectivorous bats in a cave in Pulilio Island, Quezon. He is currently involved with the DOST Nicer Caves program of the UPLB Museum of Natural History and is also part of a bat virus research program in the Philippines, which is being done in collaboration with Japanese virologists. His current research interests include wildlife biology, bat bioacoustics, ecology, taxonomy, and systematics. Friends, let us all welcome Kirk Taray. Kirk?
Thank you, Sir Flor, for that introduction. So let me share my screen. So good morning, everyone. Today, I am given the opportunity to share what I've learned uh, from the literatures that I have read to understand bat bioacoustics and from my personal experiences in conducting bat bioacoustic studies. So we will shed light on some of the questions you are probably pondering on, including what is echolocation, how do bats use echolocation, how do we study bat echolocation, and where can we apply it. So I hope that I can address these questions as we proceed with our discussion. So here are the topics that we will cover for today. So first, we are going to some of the details of bat echolocation, including its propagation, production, detection, and the diversity of bat calls, and how these variations affect or predict the ecomorphological niche of our bats. And we will also go over with the challenges that our bats need to overcome when using echolocation as their main sensory system. Next, we will tackle with how the process of call analysis is conducted. So from the equipment used to the software and statistical tests employed to analyze a bat call design. And then we will be having a brief recall of the studies conducted in the Philippines on Philippine bats in relation to their echolocation call and determining their presence or activity using acoustic monitoring. And lastly, we will enumerate some of the research areas where we can apply bioacoustic methodologies or use bioacoustic methods or information to augment research output and improve our understanding on Philippine bats. So let's now begin our discussion with the question. So what do you think when you hear the word echolocation? What do you associate it with? And in a much simpler sense, what is echolocation? So can you please type in the chat box for your answers? Okay, so echolocation is basically the use of sound to orient in space. So that's the simplest definition of echolocation. So you use sound to determine what is in your surrounding, what are the obstacles or what are the objects in front of you, or uh, the materials that you are keep you stay in your surrounding. So this is the utilization of echo. So this is the returning sound from the self-generated acoustic signal. So the echo is the sound that bounces off an object coming from your original acoustic signal. So this is mainly used for navigation, foraging, or maybe for both. And this is an entire process of using sound to detect, classify, and localize object or prey items. So in detection, you find whether the echo that you receive is contains information on your surrounding, and you classify these echoes and the information inside these echoes, and you use this information to localize where are the objects in your surroundings. So Echolocation can be observed in many animals, and here are some of the animals that are most commonly known to echolocate. So we have oil birds and swiftlets. So this oil birds and some species of swiftlets are prefer to nest in caves. So there are dark zones in the caves, and primarily your visual perception is not much of use. So they use sound for navigation in caves. So you can actually hear this uh, swiftlets, the swiftlets when they use echolocation when they emerge or when they go back to the cave they are nesting. Next, we have our dolphins and or toothed whales. So this is another group of animals that are very known to echolocate. So they produce the sound through their nasal lips in the blowhole, and they use the melon. So this tissue in front of their heads to direct this sound as a beam, uh, of course, for the sound to travel in water. And when the sound uh, hits an object, so it bounces back as an echo. And this is received by the jawbone. So there is bone conduction because the toothed whales and dolphins don't possess an external pinna, so they receive the returning sound in their jaws, which will travel to their internal ears. And bats, frugivorous bats also have a type of echolocation which is only present in a single genus, so the genus Rosetus. So they have lingual echolocation. So these are produced by tongue clicks. So these are mainly used for navigation. So I have observed this personally from an individual. So they really produce high pitch sort of peeps. It's sort of like a peep, but in a very high pitch sound. And for our focus for today are the microchiropterans. So unlike the lingual echolocation of Rosetus, so microchiropterans produce echolocation through their larynx. So they have laryngeal echolocation, just like how we produce our sounds for communications. And this is directed or emitted by either by the mouth or by the nose lift. So for those bats that have elaborate nose lift, so the function of the nose lift is to uh, direct the sound. And microchiropteran echolocation is ultrasonic, so this is beyond the human perception. So uh, our ears can only detect vibration from 20,000 hertz or 20 kilohertz. So microchiropteran or microbat echolocation is beyond that. And actually, for some of us, can hear bat echolocation. So, but only to a certain extent, and uh, just only slightly above this 20 kilohertz bar. So those bats that echolocate just above this 20 kilohertz, some of us can actually hear that. So uh, this is a spectrogram of the sounds from a Rhinolophus philippinensis individual. So this figure at the top shows a communication call. So this is, you can actually hear this as a screech or a squeak from a Rhinolophus philippinensis. And further in the recording, so at 62 seconds, so this is it shows the echolocation signal of the same species of the same individual. So uh, how do we differentiate this communication calls from echolocation calls? So first, echolocation calls are generally short duration because they are used for target accuracy and to optimize target distance. So they are generally shorter compared to our communication calls. Next, they contain higher sound energies because to uh, you want to perceive you want your echoes to be loud, so you need to send signals that are also loud in itself. And lastly, their spectrotemporal characteristics are relatively simpler compared to communication calls. So if you look at the amplitude design of a communication call, there are a lot of fluctuations. And actually, this is important because changes in the or modulations in the echo can be easily recognized or discerned as a deviation from the original. So information from the echo is embedded here, sometimes as fluctuations in the amplitude or changes in the frequency structure of the echolocation call. So generally, this is how bats use echolocation. So as I've said earlier, they use uh, uh, echolocation calls are produced in the larynx. So this is emitted through the mouth or the nostril. So uh, indicated by the blue curved line. So that's the emitted sound. So when it hits an object, so a returning echo bounces back. So uh, the sound will only bounce off an object the when the size of the object is less than the wavelength of the call. So the wavelength of the call is significant or crucial in determining the size of which the call can bounce off or can produce an echo. So this is perceived. So the echo is perceived by the ear. So for example, the bats produced a signal and the echo returned after 2 milliseconds. So how do bats determine the distance of the object relative to its position? So basically they just compute, of course they don't compute they don't perform these mathematical equations, but actually this is how they determine or estimate. So just by the equation of speed, so that's distance over time. Speed is, yeah, distance over time. So to determine the distance, so this is speed times time. So in air at 1 atm and 20 degrees Celsius, sound travels in air at 343 meters per second. So that's the speed of air in a sort of normal air condition, normal atmospheric condition. And when the return echo is perceived at 2 milliseconds, that means that the sound traveled to the object at 1 millisecond. So that's your time, 1 millisecond. So just do the computation, and so uh, the distance of the object from the bat, if it received the returning echo after 2 milliseconds, is 0.343 meters or 34.3 centimeters. So basically, that's how they estimate the distance of the object uh, from their position. Now, to fully understand how ultrasonic sounds are perceived by bats, let's take a step back and recall what is sound first. So sound is a physical entity. So sound is a wave. So it is a longitudinal wave. So this is propagated by the compression and rarefactions of molecules to which the sound travels. So it has properties. So let's define first what is wavelength. So I've introduced the concept of wavelength earlier, but what is wavelength by definition? So this is the distance between the two corresponding points of a wave. So most of the time, this is the distance between two crests or the highest point of the wave. And uh, next is the frequency. So the frequency is the number of waves that pass a fixed point at a certain time. So a wave is consists of one trough and one crest. So that's from the equilibrium. So this is one wave, and this is another wave. So frequency counts how many waves pass through a certain point. So for example, if this is your fixed point, how many waves will it travel? How many waves will travel in that fixed point for a certain amount of time. And another property is the period. So this is the time it takes for a particle to complete a cycle. So as I've said earlier, so this is one wave. So the time it takes for a particle to complete one trough and one crest, or one crest to one trough, is the period. And period and frequency are inversely related, because as the period increases, so the time it takes, as the time it takes for a particle to complete a cycle increases, your frequency decreases. And lastly is the amplitude. So this is the maximum displacement of a wave from the equilibrium. So this is what we perceive as the loudness of the sound. So that's the amplitude. Uh, and going back, so frequency, we perceive frequency actually as the pitch of the sound. So how high is the sound in terms of their pitch. So the relationship between frequency and wavelength is actually crucial in elucidating how bats sense their environment. So here in the equation, so wavelength and frequency have inverse relationship as well. So as the wavelength increases, the frequency of the sound decreases. And this is crucial in how bats can, this limits the perception of bats, the size of the objects that they can perceive. So now let's go over what consists an echolocation signals, or what are the elements. So primarily there are two signal elements in an echolocation signal, or uh, how frequency modulations are perceived in consist an echolocation signal. So we have narrowband signals. So this have very few small frequency change between the start and end of the signal. So as you see here in the figure, so the frequency does not really actually change very much over time. And this is best suited for detection of echo. So if you have, uh, if you produce signals with, uh, if you produce signals with narrowband components, so they are typically produced in long durations. So your you can detect echo much more with a narrowband signal, because this persists in your detection range much longer. And we have two types of narrowband signals, which are quasi-constant frequency. So this narrowband signal changes a few kilohertz over time, while constant frequency narrowband signals only change by a few hertz. So for quasi-constant frequency, that's kilohertz. The small change is in kilohertz, while in constant frequency, it's just in hertz. And the next type of signal element are broadband signals. So uh, they have large frequency change between the start and end of the call, and they are actually frequency modulations over a short period of time, and these are best suited for uh, marking time. So they are precise time markers. So if you hear the echo coming from a broadband signal, so you'll so the bats can perceive that, okay, uh, I've received, or I've perceived this sound at this exact time. So compared to broadband to narrowband signals, so these are less suited for time marking, but best suited for detection of the echo. And bats producing narrowband signals, especially those that producing constant frequency signals, produce their calls at high duty cycle, meaning that their echolocation calls are produced in long duration and short interval, uh, while bats producing broadband signals have produced calls at low duty cycle, so very short duration calls and very long interval. So, so narrowband signals and broadband signals can be present in a single echolocation signal, so that creates the diversity in echolocation call design. So we can have just a pure FM call, or a call with CF and FM components, or multiple or a more complex call where there is an FM component in the beginning, a long constant frequency component in the middle, and a call that the call that ends in a short frequency modulation. So this is possible. So this variability is possible because of how bats produce the calls. So frequency modulations is due to the timing of the glottis opening in the larynx, which is simultaneous with the or in sync with the contraction and relaxation cycle of the cricothyroid muscles. So this is the muscle which is responsible for the ultrasound, for the capability of the bats to produce an ultrasound. So the diversity in echolocation calls is not limited with its design. So echolocation calls also varies in their spectrotemporal characteristics to the point that each species has a distinct uh, set of call characteristics. So as you see here in the figure below, so this is the echolocation calls of from A to C. These are pure FM calls, but from 3 different species. So here with uh, 5 species producing calls with constant frequency uh, component in their call. So the limitations or the diversity in the echolocation is not just limited with the design, but also with how the spectral and temporal characteristics of the call define each echolocation call. And uh, this enables bats or this allows bats to uh, occupy various ecomorphological niche. So this depends on where the bats prefer to forage or where they get their food. So first are the open bats. So we have bats that prefer to forage in uncluttered spaces. So high above the canopy or high above the ground, or just any spaces far from any vegetation or from any objects where their calls can bounce off. So these bats are typically your fast flying bats because they don't have any objects where they can collide or where they will collide. Next, we have edge bats. So these bats prefer to forage and hunt for insects or other prey items uh, near the edge of the vegetation or vegetation gaps, also near the ground or near the water. So this includes your trawling species or your fishing bats. And lastly, we have narrow space or closed space bats. So these bats prefer to forage in highly cluttered environments. So a lot of objects that can interfere with the echoes. So that's where they prefer to hunt. And their wings are usually short and blunt for more maneuverable flight. And also some of them fly in a slow fluttering manner. And even though bats have varying ecological niche, this doesn't limit them to make use of the available resources. So uh, bats take advantage of all the resources available to them. So the elasticity in bats adapting to varying environment to take advantage of the available resources is made possible by the changes in the echolocation signal. So by the figure here, the bottom figure. So we have species that can forage or hunt in different uh, cluttered environment. So for example, our Myotis. So these species have been observed to uh, forage in open space, in edge space, and even in highly cluttered spaces. So just by changing the characteristics or the design of their calls, they are able to take advantage of the environments and the resources in that environment for survival. So that so now that we have differentiated bats according to their ecomorphological niche, their echolocation signal, and their echolocation signal. So uh, let's take a look at how do they effectively hunt in their environment. So there are several foraging modes for on how bats uh, hunt their food or take their food. So we have first aerial hawking. So these bats are those that capture food mid-air. So they usually feed on actively flying insects. So just like Meotis lucifugus, so they take uh, flying insects, or for in this case, a moth, mid-air. So they snatch their food mid-air. Next, we have gleaning. So this is a type of foraging that where bats pick up their food from the ground or any surfaces. So they usually this gleaning mode usually accompanies uh, detection of prey in prey produced sounds or other sensory systems. So they just don't depend on the echoes that they produce. And lastly, we have trawling. So this is a specialized gleaning foraging mode. So this is sort of gleaning in water. So we have trawling species where they prefer to, or they can scoop up insects or even fish from water. So this is a specialized gleaning. So they have other adaptations to get their food from water. So some have a very long nails or uh, tarsal bones just to scoop out the food from water. So that now we've looked into the variability of echolocation in terms of their design, the spectral-temporal characteristics, and how do these bats use to hunt food in their environment. So let's see, there is one more type of variability in echolocation, which is related to their behavior, especially in feeding. So bats also change their echolocation according to the information they receive, especially during feeding. So we have search phase types of calls. So search phase types of calls are typical pulses for commuting, just for moving around and for searching of prey, of course. So this is what we actually use for call analysis. So search phase calls, because these are sort of the standard calls that the bats produce. So when they receive an echo indicating that there is potential prey, so they shift their echolocation calls to approach phase. So this is the time when they select the target, and they produce much steeper calls and in a much shorter duration. So they produce calls in that have that have steeper frequency modulations, and in a they and is produced in shorter interval compared to the search phase calls. And when they reach, or when they approach or locate the prey that they want to capture, so they shift again their echolocation into a terminal to the terminal phase, or what we commonly know as the feeding buzz. So this is a faster call production, a much steeper frequency modulated calls, and actually this is critical for feeding decisions. So during this time, this is where they decide if they will get the food, and they need to produce calls at a faster rate, because they want to be updated on the characteristic of the prey that they are trying to hunt. So as we talk about how bats vary their echolocations in terms of behavior, and in terms of also how they use the environment. So let's now go over with the challenges that they need to overcome uh, to or they need to overcome to by when using echolocation as their main sensory system. So, so well, as a sensory process, auditory perception also has its own challenges, much like visual perception. So we have uh, masking, Doppler shift, and attenuation uh, challenges that our bats need to overcome. So let's first define masking. So this is when masking happens when other signals interferes with the evaluation or processing of the target echo. So sound will not only bounce off the prey item that the bats wanted to detect. So it will bounce off on any object that the sound will reach. So we have forward masking. So this is when your clutter echoes, so the echoes or the noise coming from the environment, the unwanted echoes, comes first or is detected first before the target echo that you want. So, for example, in this case, in the a figure on uh, on your left. So in figure C, so the white the white figure here indicates the clutter echoes. So in C, as you can see, there is forward masking happening. So you receive first the the clutter echo before you see before you perceive the target echo you are wanting to or you need to evaluate. Then there's backward masking. So this is produced when the signal follows the clutter echo follows the target echo. So this is what you see in B. So masking is a more common problem to bats producing calls at low duty cycle, as I've mentioned earlier, because they avoid self-deafening by differentiating or segregating their signals from the echo in time. So they don't simultaneously produce their echolocation call and perceive the echoes coming from their self-generated signals. So they overcome this by uh, computing for the overlap window. So in the figure here on your left, yes. So there is a distance to which the echo or there will be no overlap between the uh, clutter noise and also your self-generated signals. So they have to determine there's overlap free window to overcome this masking problem. So next is our Doppler shift. So this problem is encountered when bats are moving because when bats hunt, of course they move. So the Doppler shift is a phenomenon when there is a change in the wave frequency during the relative motion of the source and the observer. So, for example, in this case, in as you experience Doppler shift when, for example, you hear an ambulance. So, an ambulance that is coming towards you sounds a bit at a higher pitch compared to the ambulance that is going away from you. Uh, so the returning echo from moving bats actually is received at a higher frequency because of this, because bats move towards the source of the echo. So as you can see here in this figure, so as the bats move closer to the source of the echo, so the wavelength or the wavelength of the echo produced decreases, so increasing the frequency of the wave. So Doppler shift is compensated by bats producing CF constant frequency signals. So since the returning echo is always perceived at a higher frequency, so they produce their own signal at a lower frequency so that they can still hear the returning echo at that sweet spot because bats producing calls at with constant frequency components actually have auditory fovea. So this is the sweet spot in the ears when, and they can only hear at a very small range of sounds because they are producing constant frequency. So they don't need to hear uh, sounds beyond that frequency value of their CF component. So to compensate for that, for the Doppler shift, because Doppler shift increases the frequency of the returning sound. So the sound that they produce, so the sound that they produce is in a lower frequency, so that when it when the echo is affected by the Doppler shift and it is changed into a higher or converted into a higher frequency echo, they would still hear those returning echo. And lastly, we have atmospheric attenuation. So this is the reduction of sound amplitude or the energy in the sound as the sound travels through air. So this is mainly by the scattering of the sound or by the absorption of the molecules uh, comprising the air. So there are several factors that is considered in atmospheric attenuation. So first is the sound frequency. So typically higher frequency sound are more prone to attenuation because uh, atmospheric conditions act as a low pass filter. So there is a threshold set for by the at this combination of atmospheric pressure and uh, frequencies below that threshold are not attenuated, but frequencies above that threshold are exposed to attenuation. So again, so higher frequency sounds are more attenuated than low frequency sound. So next is temperature. So the increase in temperature actually, uh, of course, cause the excitation of air molecules. So increase in temperature results to more energy absorbed by the composing molecules from the sound. So that's why the energy in the sound decreases. This is absorbed by the comprising molecules of air. Next is humidity. So moist air is actually less dense than dry air because water vapor is less dense than the molecules comprising air. And that means that sound will travel faster in moist air. And when sound would travel faster, then there will be again more energy absorbed by the molecules in the air. And uh, last is the air pressure. So sound, as we've discussed, as I've presented in the previous slide, that there is that propagation of sound is dependent on the contraction and rarefactions of uh, air particles. So air pressure, the increase in air pressure, or how compact your air becomes in the environment, decreases attenuation because your sound will propagate more in a more compact air because uh, your sound will depend on the proximity of the molecules from which it will propagate and travel. So now that we have gone over the diversity of bat calls and the challenges that they overcome to when using echolocation as a uh, sensory system, now let's take a look at how do we study uh, bat echolocation calls, and we'll go over from the recorders, the softwares, and the statistical tests employed in conducting call analysis. So ultrasonic recorders, or what we usually call them as bat detectors. So these are recorders that are capable of recording high frequency sounds. So there are different types of bat recorders out there in the market, but I'll present three common bat detectors that are available. So we have heterodyne detectors. So this converts calls into audible sounds because ultrasonic sounds are inaudible, right? And with this type of recorder, they convert the ultrasonic sound by adding or subtracting the base frequency from the recorder. So the recorder has a base frequency, and when an echolocation call or an ultrasound is recorded in that bat detector, it will add or subtract uh, the uh, the base frequency from the ultrasound recorded and convert it into uh, an audible sound. So this heterodyne recorders usually present uh, audible sounds in real time. So uh, you can actually hear them while you are recording. However, they can only offer a narrow frequency range because there is, as I've said, there's a base frequency from the recorder. So every uh, higher frequencies can't be converted into audible sound anymore. So there is a limit to the frequency that the heterodyne detectors can convert into audible sound. And also, you always need to retune your recorder. So this is actually not helpful when you are trying to detect bat activity or determine what bats are flying around you or what bats are present in your area. So next one, we have zero crossing bat detectors. So they record frequency over time output every time a sound wave crosses a set 0 point. So there is a threshold frequency that is set here. So every time an ultrasound uh, reaches that 0 point, it will be recorded. So this is good, and this is good for remote data collection because you can leave most of zero crossing bat detectors, you can actually deploy them and just leave them on site and retrieve them when the battery runs out. So this is very good for long-term surveys. However, however, they don't have or they don't record harmonic and amplitude information. So they just uh, record the strongest frequency at one time. So harmonics or other, for example, you have more than one bat passing through that detector, so it will only record the frequency of the bat that is the strongest. And uh, that's why they contain less, actually they contain less information, but actually these detectors are uh, good in studying bat activity in an area. And lastly, we have our full spectrum bat detectors. So this detectors records original, unaltered frequencies and full spectrum range. So they are sort of recording all the information that can be gathered from an echolocation call. So they can be real time for your handheld microphones, and of course sorry they pack a lot of data, even metadata, so GPS position, temperature. So these kinds of detectors can record that. However, since they have full pack data, they record a lot of information. Uh, they also need they consume large uh, actually, sorry, they consume large file sizes, and they are relatively more costly than our zero crossing bat detectors. So we have different types of bat detectors. Therefore, we also have different types of recording files that are coming from these bat detectors. So first are our sequence files. So these are zero crossing files. So one file is saved for each bat pass. So a bat pass is uh, considered as uh, one individual passing through that detector. So usually, for example, this is considered one bat pass, so this is attributed to one individual bat. And this files usually ends in .zc, so meaning zero crossing, or number hash. So this indicates the number in uh, the number of the file relative to the entire recording of recording in one night. Next, we have ZCA files. So these are uh, only found in Anabat Express. So the zero crossing bat detector that I have that I have given as an example earlier. So they record this. So they save one file per night. So for example, this one. So sequence files only record one bat pass per file. But in this one, you can have multiple bat pass as long as they are recorded the same night. And you need to convert it actually before you can analyze this, you still need to convert this into sequence files. So this ends actually, the file ends usually in ZCA, so that's zero crossing for Anabat detectors. And we have our waveform files. This is for full spectrum. So as I've said earlier, they are full pack of data, so you can have harmonics like in here, and you can actually also hear or record other sounds, other noises. In this case, these are sound of insects. So you can record the bats as well as the insects for this case. So full spectrum bat detectors offers a lot more data and more analysis than any other bat detectors. So let's now go with the softwares or what we can use to analyze, view, analyze, and manage our call recording. So we have C-Wave. So this is a free software. You can download it and it's free. And they support the Dotronic ultramic detectors. And actually, I have tried to open uh, recordings from other bat recorders here, and actually it supports the recordings from other bat detectors as well. So they can, it depends on the recorder on uh, how uh, how much frequency you can view. So if you only have a Dodotronic Ultramic 250, so you can only have 125 kilohertz of view from the bat detector. So next is from the Peterson. So we have bat sound. So this is actually this is exclusive for Peterson Electronic. So this uh, this is used for recording. Actually, this is used for analyzing calls. You have a separate uh, software, which is Bat Sound Touch, which is used for the recording when using handheld microphones. So they store they you can open in this software WAV files or waveform files or even MP3 files. So they have automatic parameter extraction, so you can automatically see frequency values here in the analysis mode. And this is Windows compatible. If you're using Linux or Mac, Mac OS, you need to have that crossover uh, software to be for you to be able to use Bat Sound in Linux or Mac OS. Then we have Kaleidoscope from Wildlife Acoustics. So there is a free version of Kaleidoscope, which is Kaleidoscope Lite. It offers limited functions, but you can still identify bat calls, measure bat calls, and do other analysis with that. But if you want other functions such as cluster analysis and sound pressure level analysis, you need to have that Kaleidoscope Pro. So that is, you have to subscribe for that software. So what's good with this Kaleidoscope is there is a bat analysis mode. So you have separate analysis functions for bat call recordings, and they offer zero crossing and full spectrum analysis. And lastly, we have from Titley Scientific, Analog W. So this is what you use for Anabat Express to uh, to study, manage, and view the recordings that you have from Anabat Express. So this is also Windows based, and uh, I think you need the crossover software again if you want to use it in Linux or Mac OS. So this has multi-document interface, so you can look at a lot of files at the same time, and you can manual input other information such as GPS, or in this case, you can add species labels, so you can label the species using these tabs here. So uh, the use of the software is actually depends on what you are trying to study. So call characterization is actually a fundamental work when dealing with bat acoustics to describe your calls, especially with our setup here in the Philippines, since we don't have call libraries for our bats yet. However, you can still do other analysis using bat call recordings without doing call characterization. But if you want to know the activity, the presence, the behavior of the bats, of the specific bat that you are trying to study, this step is really a must. So in call characteristics, you measure uh, several characteristics of the call. So what I have done so far is measuring 7 characteristics divided into 2 groups. We have spectral characteristics that is actually related to the frequency. So these are frequency related characteristics. And we have temporal characteristics. So these are time-based characteristics. So of course we have start frequency. So this is the frequency registered at the start of the call. We have end frequencies. So this is the frequency at the end of the call. Sometimes minimum and maximum frequency can be uh, measured along with end or start frequency, depending on the structure of your call. And lastly, we have peak frequency. So this is the frequency with the maximum energy. Sorry. So this is the frequency component where most of the energy of the call is contained. So for our temporal characteristics, we have uh, duration. So how long does uh, a bat pulse is produced, and also have interpulse interval. So now that we have measured or and record the call characters, we can subject them to descriptive statistics by getting the mean, the standard deviation or standard error, uh, and look into each character or how each individual of a species deviate from the mean. We can also perform t-test and ANOVA test to determine variations between and among species that you are studying. Or you can test how distinct the calls you have recorded, and can the combination of your call characteristics be used to predict or group your species into distinct groups. So that's where discriminant analysis comes into play. So this is a statistical technique used to classify calls into overlapping groups based on the scores of one or more call characteristic as predictor variable. So basically, discriminant analysis seeks out the best linear combination of the call characters to maximize the difference between each group, in this case, your species. So you use the call parameters to delineate the species or the grouping of your species. So this is based on eigenvalues produced from canonical analysis. And you actually use Wilks. You also have Wilks lambda statistics in this test to determine which of the parameters or the call characteristics have the highest influence on the discrimination of your group. So just like here, so just like in this graph, so Using the call characteristics, we define each group as this either distinct or are they similar or how close they are together. And uh, discriminant analysis also offers a confirmatory test whether your prior classification of species fits with how the analysis groups a group or group your uh, samples according to the characters that you have used as predictor variables. So now let's go over with the what has been done in the Philippines in terms of bat bioacoustics. So let's start with the studies of Jody Sedlak. So I think this is the first record for her study on Mount Makiling is the first record of bats with that reported the call characteristics of the bats. So she used anabat detectors to record hand release, uh, uh, free flying, and handheld bats. So she recorded minimum frequencies, maximum frequency, and the constant frequency component of granulophage. And with this, she recorded some uh, call characteristics of 16 bat species. And with her another study on uh, the ca- the bats the bats living in the karst areas in Bohol. So she used another type of bat recorder. I'm not familiar with this, but this is from Avisoft Bioacoustics. So ultrasound gate 116. She recorded calls from handheld bats and also free flying bats, and determined the peak frequency of the bats she recorded, and uh, in total she recorded the peak frequency of 12 bat species. Next, we have the report of Anthony Mold. So this is his study in Panay Island. Actually, the bioacoustic part of uh, uh, his study is just for the confirmation of species that uh, uh, he did not really actually observe physically. So he used the echolocation calls to uh, distinguish which species are living in these areas. So he used bat box DeWitt frequency division bat detector. I'm also not familiar with this bat detector, and using bat sound to analyze the calls, and uh, he measured the frequency range. So that's what he uh, recorded from the echolocation from the recordings that he had. So next is the master's thesis of James Alvarez. So he studied the diversity distribution and activity of bats in Mount Giting-Giting National Park in Sibuyan Island. So he used a lot of bat detectors in his thesis. So he used Peterson uh, full spectrum bat detector to characterize the calls, and use Anabat Express to record the nightly activity of bats. So as you can see here, he described the calls of 10 bat species, and in this figure, uh, he differentiated the nightly activity of bats depending on the season and the elevation from which he recorded the bat activity. Next is from the thesis, turned into a publication of Frex de Maculangan. So he used Anabat and SM4 bat detectors, also Dodotronic ultramagnetic detectors to study the seasonal emergence of bats in Mount Makiling in a cave roost, in a rock crevice roost. So he determined peak frequencies of the bats uh, roosting in that area, and with the seasonal emergence counts, he found out that uh, some species like Rhinolophus inox and Rhinolophus arcuatus use this rock crevice as a maternity roost because of their high activity in the cave roost during the breeding season. So next is the study of Fidelino and Gan, where they studied the activity of bats in uh, urban green areas. So specifically in Diliman campus. So they did not describe the call of the species, but just actually put the detectors in field and uh, record the activity of bats and group uh, the recorded calls into a sonotype. So they have recorded seven sonotypes, which I presume would be equivalent to also seven different species of bats. And next is what I did in my thesis. So I studied the echolocation call and emergence patterns of bats in Polillo Island. So in the cave that I studied, there are 5 cave-dwelling bats. So I described the calls of 5 bat species and used these calls to study the emergence pattern. So in the emergence pattern, I determined uh, the order of which the bats emerge from the cave. Is there an order? And if there is, what affects this? And also, are there changes in the timing of bat emergence? Do they emerge in times where there are more rain or earlier sunset? So I found out that precipitation, atmospheric pressure, and sunset time actually affects the time of emergence of bats. So they actually emerge sooner uh, when the sunset time is earlier. And lastly, we have the recent publication of Pangerong on the bat calls of that calls recorded in Bulacan. So I think this is the first and only publication in the Philippines that really focused on describing the echolocation calls of Philippine bats. So she used Peterson M500 recorders to record the calls of 15 bat species. So these are she recorded it by pre-releasing the bats in an enclosure. So I presume these are large tents. And in her studies, she also uh, compared her results with other existing call records, especially with the information from Jody Sedlak. And she also did discriminant analysis to determine whether her calls or whether the call characteristics of her bats is enough to delimit or group the species correctly. So now let's go with where we can the applications of bat bioacoustics methodology, or where we can apply uh, bat acoustic information. So we can use this in biodiversity research. So just like these 2 studies where they uh, use the bat detectors to determine the activity, the richness and diversity of bats in these national parks in Africa. So in this first study by Kirk and Bernard, they actually presented the first assessment in that national park for the bats, and they detected 11 species through the bat detectors. In this study by Dalhomi in 2020, so they actually use mixed methods. So there's capture, there's misnetting, and of course there's acoustic recording. And through acoustic recording, they've detected 6 species. So we can use this to determine what species do we have in a specific area, or are the numbers of our bat species changing with the changes in the environment. So next is ecological studies. So we can apply bat bioacoustics method to study the ecology of bats. For example, the response to changing landscape, just like in the study of Villarroya-Villalba on the response of bats in uh, green spaces in Europe, which she found out that actually there are activities in green areas in Europe, especially with the major cities. So there are still bat activities. However, the artificial lighting in the green spaces affects or decreases the activity of bats, maybe because they are not uh, adapted yet to the lightings in the urban areas or urban green spaces. Next is the study, the feeding ecology or foraging ecology study of steel shock. So uh, using using a series of acoustic recorders, so they determined that uh, bats actually use eco guided information to capture their prey, and they are best example of predators that have control over their sensory system to catch uh, evasive prey. So we can also use this to study bat activity and behavior. So a study by Jody Sedlak on the activity of bats at different growth stage of rice. So she found out that there are more edge space bats uh, that are actively hunting in in the rice paddies during the early growth stage of rice, and her study actually is important uh, indication of the importance of rice-dominated environment for bats, and the importance of bats as consumer of insect pest of rice. And this study of seamers on the trolling bats. So they found out that trolling bats would likely hunt for prey in calmer water because calmer water bounces off an echo much clearer than turbulent water. And in clearer waters, the glints or the information about the prey is not embedded with the clutter echoes. Next is we can also use bioacoustic information in taxonomy and systematics. So this study of Taba in 2006. So they determined bats previously uh, identified as one species, so Hipposideros larvatus. Uh, the population in this single cave uh, produce bimodal distribution of frequency. That means they have different peak frequencies, and after genetic uh, sampling of this population, they found out that those two diverging those individuals with varying peak frequencies have 12 to 13% sequence divergence. And by comparing the genetic sequence of uh, these bats from other local of comparing the sequence of these bats of the same species from other localities, they found out that the 98 kilohertz bats form monophyletic group with other uh, population, and the 85 kilohertz bats is actually in consideration to be a distinct and separate species. Next is the study of Kingston on Hipposideros bicolor. And what's good with this is that this was uh, 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 further elucidated in uh, a much later study by Murray. So here, Kingston and his colleagues studied the divergence in call frequencies of Hyposideros bicolor, and they found out uh, bats also uh, exhibit frequency bimodal distribution of frequency, where there are 100 bats producing at 131 kilohertz, and there are bats that producing calls at 142 kilohertz. By determining the cytochrome B sequence, so they found out 7% divergence, but uh, the the difference in the uh, frequency characteristics of their calls are actually not for resource partitioning of detectable prey, but for difference in microhabitat use. And uh, the study of Murray later on in 2018 uh, further established that the Hyposideros bicolor 142 kilohertz bats is a new species, and the other one is retained as Hyposideros bicolor. So we can also use this for conservation studies. So for monitoring bats and how do uh, how do changes in landscape uh, affect the activity or even the presence of bats, just like the study of Wong. So they determined bats that are tolerant to coffee agriculture, and there are also bats that are sensitive. So these bats are those that really rely on forest to survive. So there are a lot of applications where we can use bioacoustic methodologies and bioacoustic information. However, in our case here in the Philippines, these are the studies that actually we still need to do. So we need to build a call library for our bats. So uh, that can be done by characterizing the calls of uh, our bat species and determining to what extent do they apply, or to what extent do they vary from each population, or do they uh, retain the characteristic uh, in different environments. So we need to describe first our the cause of our bat species, so we are able to use this bioacoustic information in other research areas. So as of now, we have 29 species with at least one call characteristic recorded. So from 7 insectivorous bat families, we have records from 5. So we still don't have any record from uh, molluscid bats and from the family Megadermatidae. So I actually have a record of the call of Megaderma spasma. I just I'm just finding time to characterize them. So at the moment we have 29 species with at least one call record. And so that's the end of my talk. So before I give uh, the floor again to our host, so I would like to acknowledge first some institutions and people that helped me to develop this skill and understanding on bat ecology. So first, to the UPLB Museum of Natural History for giving me the opportunity to share my knowledge about bat echolocation, and also for supporting my thesis by providing me the materials that I needed to record bat calls and their activity. And also to Bio 154 Cave Ecology. So I would like to plug and endorse this course to everyone. So if you're enrolled in UPLB, so please, when the face-to-face class will resume and you still have extra courses that you can take, so please take cave ecology class. This is a really good course where you will be immersed in a new environment, especially that this class focus on the cave environment. And I would also like to thank my thesis advisors, Dr. Juan Carlos Gonzalez and Dr. Erneo Elliott Jr. for the continuous supervision during my thesis, for all their help uh, for me to finish my thesis. And I would like to give special thanks to these two people. So to Professor Philip Alviola for taking me under his wing and really mentoring me to study bat echolocation. So thank you, Sir Philip, for giving your time and effort to really teach me and give me directions and uh, supplement my knowledge on bat echolocation. And uh, to more studies about bats with you, sir. And lastly, to Sir James Alvarez, who started the study of bat echolocation in UPLB. So thank you for starting this research here in UPLB, and I hope we did justice when we finish the study that you have started. So thank you, Kuya James, and actually he is uh, he has taught me a lot, even though uh, we did not see each other physically. I learned a lot from his other seminars when he was still alive. So thank you so much, Kuya James. So here are the references that I used in this talk, and thank you very much.
All right. Thank you very much, Kirk. Very comprehensive presentation. Is para lang tayong nag-crash course ng bat echolocation. All right. So we'll have just a few announcements. Mawawala lang saglit yung ating speaker because meron lang siyang connection problems. And while we're taking the quiz, they will be reconnecting in a few. So let me just wait. Let me just share my screen. Let's start. Okay. So we have 7 questions. And first question is, what is an ultrasonic wave or an ultrasound? So you have 5 options there. And if we have some of the options we need to clarify, we will ask Kirk. All right. And around 40% of you answered all of the above. Let's see the yes, and the answer is D, all of the above. Our next question is, what is the genus of the theropodid bat that reinvented echolocation by using tongue clicks to generate sound for navigation and or orientation? We have Unicteris, Megaderma, Nyctimini, Sileps, and Rosetus. And time's up. And I think, wait, we have 29% answering Rosetus. And I guess, let's see. Yes, 29%. It's Rosetus. It's the genus of Rosetus, no? That can do the tongue clicks. Third question, what is or are the types of a broadband signal? Para pala tayo nag-physics na ito, no? Constant, frequency modulated, quasi-constant, both A and C, and all of the above. Oh, we have an option, none of the above. Okay. And the people answered both A and C. Let's see. It's frequency modulated signal. So, Kirk, can you explain?
So actually, broadband signals are those signal elements that have a broad bandwidth. So given by the name of the two options A and C, so constant frequency and quasi-constant frequency, that actually is a almost a given that they are narrow band signals. So they the changes in their frequency components is very small compared
Mhm.
to our broadband signal, which is frequency modulated.
All right. Thank you very much, Kirk. Next question. Which of the following is a type of foraging mode described as a specialized gleaning in water? It's towing, trawling, and throwing. Trolling, towing, trolling, and throwing. May tongue twister pa tayo dito, right? And let's see kung sino yung mga... Okay, trolling, 68% answered, and 68% of you got it right. Okay. Fifth question, which of the following is not a type or a feature of a bat detector? Okay. So amplitude expansion, heterodyne, frequency division, full spectrum, and zero crossing. Parang hindi na siya biological terms. Correct, no? So dapat kaya electrical engineer ka rito, no? Alright. Sige, okay, heterodyne. 35% of you answered that. And let's see. It's amplitude expansion. Kirk, explain.
Actually, tama po si Sir Flor na usually mga questions dito hindi na bio-related kasi yung call analysis is mainly a lot of physics, daming physics na kailangan. So
Mm-hmm.
regarding this question, a lot of answered heterodyne. So actually, heterodyne is a function of most modern bat detectors, as I've also indicated, or as I've discussed earlier, that there are also heterodyne detectors. The answer is amplitude expansion because uh, there is no feature that can expand the amplitude of the call. So the, you can only analyze the amplitude of the call that you received. You can't modify the amplitude of the you can't modify the amplitude of the call that you record. So there's actually no feature such as amplitude expansion. And actually, I think I didn't elaborate on these features of a bat detector earlier. So
Okay.
that's my fault. Sorry.
Okay. No fault taken. All right, next, sixth question. Which of the following is a potential field to apply bat bioacoustics? We have taxonomy and systematics, conservation, biodiversity research, ecology, and the last option is all of the above. And 5 seconds to go. I think would be an easy peasy. Oh, I'm sorry. Okay, let's go back. I think, but the okay, wait. All right. So the answer should be, oh, okay. Anyway, let's start the last question. Oh, the answer is 96%. Okay, hindi ko nakikita, no? All right. So congratulations, everyone. And all right, the last question. How many species of Philippine bats have at least one call characteristic already recorded, measured, or described? You have 21, 35, 29, and 15. All right, time's up. And we have almost 50% of you. Wait, let me check again. 43% of you answered 29. And the answer should be 29. Thank you. And we have Jeff answering 5 out of 7 in 1 minute and 9 seconds. I think ito ang pinakamahirap na quiz so far sa BSS. Walang naka-perfect. All right. And the hardest question is, as shown here, yung tungkol dun sa broadband signal. So maraming salamat and congratulations, Jeff, for topping our quiz. All right, so let's proceed to the open forum, and I hope meron na mga questions here. I know we've kukunti na lang ating time, but let's try to answer some of these questions. So, first question is, what do you think? Can you tell us the importance of capturing the bats first before conducting your acoustic monitoring?
So capturing bats is essential to record your reference calls. So if you're just starting to do bioacoustics research on your area, so first you have to establish what are the bats in there. At the same time, what is the call characteristics of those bats. So you need to capture first those bats to associate the identity of those bats to the echolocation signals that you'll record, so that when you do passive monitoring studies, or when you just deploy your passive bat detectors, you'll have a reference on the, you'll have a reference when you do analysis on those recordings from those bat detectors. So that's why capturing bats is really necessary uh, in describing bat echolocation calls.
All right, thank you. And have you started comparing calls of the same species coming from, the ones that you are holding by your hand, using your hand, recording it, and those with you have recorded during cave emergence? So will they be dramatically different, or would they be at least very similar? Would they be similar?
Uh, so as I've discussed earlier, some of the challenges that the bats need to overcome when when using echolocation as their main sensory system. So there's atmospheric attenuation. Um, there can be some changes or some variation when you record bat calls by handheld, or when you record free-flying bats, especially during cave emergence. But I haven't tried to compare those two different recording styles yet. But of course, I have the data at hand. So given time, maybe I'll do that. But if there would be difference in the characteristics, especially with the frequency characteristics of the call from the same species recorded in different uh, recording methods or recording style. So I think
Mhm.
it would be very small or non-significant. Well, that still depends on the condition when you during the time you record the calls.
All right. So from Risian Lapus, the question is, how accurate is determining call characteristics uh, in identifying bat species without relying too much, or without relying on molecular analysis?
Oh. So uh, uh, describing calls or call characteristics is actually offers little to no phylogenetic evidence to your bats, because as I've mentioned earlier, bats vary their calls depending on their environment. So uh, you can you can still uh, uh, classify your bats using the calls, but this is not you can't use bioacoustics or the echolocation descriptions as your main evidence to delineate your species, because still molecular data is uh, a more powerful or a more robust evidence in delineating your species. But when just using in the field, or when you want to use bioacoustics data in determining the species composition, so I think that would be enough evidence to support that you have this level of diversity in bats, you have these different kinds of bats in your area.
All right. Thank you. Um, we have a question from Tristan Senarillos, and hi Kirk, congratulations. And question is that just like with other vertebrate groups like birds and amphibians, researchers encourage citizen science to record their call recordings and to submit them to a call library. No? Especially yung sa last part ng presentation mo kanina na you've managed to say that wala pang ang extensive bat call library ang dito sa Philippines. So he asked, do you think applicable ba ang citizen science in bat acoustic research?
That's a no. For now, that's a no because bat detectors are expensive compared to recording calls from birds or frogs, which are audible sounds. You can record them using your phones, using simple recorders. But with bat echolocation, you really need sophisticated ultrasonic bat detectors or those microphones that can record high frequency sounds. So in citizen science, you need of course, participation from people to contribute to develop your call library. But as of now, because of the prices of the available bat recorders, I think it is not that very applicable, except for cases if you have people who have a lot of money and just uh, buy or provide bat detectors and record calls from their vicinity and submit it to you. So that would be possible. But for the general public to contribute in developing bat call library, I think it can't be done at this moment because of the prices of the available bat recorders in the market.
All right, thank you. So do you have any more questions from the audience? Again, you can check your chat boxes, and I've managed to put the link to the evaluation of our webinar there. Just click on the link so that you will be directed to the evaluation form. So we still have 15 minutes to go. You could still ask your questions. And while I wait for more, Kirk, let me ask you, mayroon akong mga sinulat dito while you're out presenting. And you've managed to present earlier that you said that the Rosetus genus produced the echolocation through tongue clicks. So, but you didn't say how many or where. Lahat ba ng mga species under Rosetus are able to do the tongue clicking? And if so, or if not, why so?
Okay, so lingual echolocation in the genus Rosetus is only documented in 3 species. We
I
have
see.
Rosetus aegyptiacus, and there's one other species I forgot the epithet. And for in the Philippines we have Rosetus amplexicaudatus. So I think this reinvention of lingual echolocation is it depended on the bats or the species of bats. So I don't think that this is related to the proximity of their phylogenetic relationship to each other. So I don't think that a specific group of Rosetus just diverged to produce lingual echolocation. I think they developed it to uh, navigate their environment, especially for Rosetus amplexicaudatus, who's dependent on caves for their roosting site. So to navigate in that very dark area, so visual perception is, I think, at a disadvantage. So they need to use other sensory system to navigate in their preferred habitats.
All right. And we have Sir Philip Alviola commenting,
Ayan.
it's Rosetus
Lesionolti, yeah.
lesionolti.
Rosetus
Okay,
lesionolti.
one of the 3 Rosetus species that can do tongue clicking, echolocation through tongue clicking. And before we go to this question by Kevin Ryan Pangan, let me just follow up my question so that it would be a bit related. So I just want to be clarified. Can bats simultaneously emit communication calls and echolocation calls? Or meron ba silang pattern? Hindi. Yeah.
So I think there is they don't produce simultaneously the echolocation calls and the communication calls, but they can adjust uh, uh, and separate this echolocation and communication calls in time, because both echolocation and communication calls are produced in the larynx of the bats. There are just different muscles involved when they produce echolocation, and when those muscles are not used, so that's when they use communication calls. And usually bats forage alone, so they do hunting individually. So I don't think that they need to communicate while they hunt or while they forage. So, well, that still depends on the context of, are they hunting near other roosting sites? Are they hunting near other species? But uh, echolocation calls and communication calls, you don't actually uh, are not produced simultaneously.
All right, thank you for that clarification. And we go to Kevin Ryan Pangan's question. Can you share with us your experiences in cave ecology course?
So, as I've endorsed earlier, the cave ecology course. So there's actual field work when I enrolled in cave ecology. So we visited two caves, two separate caves. We visited Biak na Bato and Pulillo caves. So uh, in the course, you are and actually in the field, we really apply what we've learned in the laboratory exercise, mapping caves, determining the species that inhabit the caves, from the arthropods to the vertebrates. And if you want to immerse yourself into a different environment, especially that it is a cave, so it's a subterranean habitat. So take cave ecology course and gain your personal experience in the course.
All right, thank you very much. I hope I don't know if Kevin is enrolled at UPLB, but should you have what do you call this? Should you take your MS here in UP Los Baños, probably you could uh, also get the chance to take cave ecology in the future when we have the face-to-face and the the guidelines in conducting research and student requirements and activities outside of your is already relaxed. Okay, so any more questions from our audiences? Reminding everyone to evaluate our webinar to get your e-certificate. And it's 11:50. I think we could just accommodate one or two more questions before we close our program. And okay, let me just ask my last question. Just wala lang. I was just curious kasi like do you have some sort of ideas, no? Where that where you we can take the advantage of bat loc bat echolocation, wherein can we will be able to some sort of modify our observation of our observation environment so that we could probably capture them easier, uh, or probably monitor them better. It's like parang if they use bat echolocation, echolocation to navigate and to ensure that hindi sila makakapture. Kasi napansin natin yan, nakita natin yan, di ba? When we are out in the field and we are using mist nets, sometimes kita naman natin, babangga na sila sa mist net, nagagawan pa nilang um, makataka. So, I was just wondering, ano yung mga pwedeng ideas natin na pwede natin gawin, modifications during our monitoring activities, things that we could do para to increase the likelihood of capturing them or monitoring them.
So for capturing bats, uh, there's actually a specific distance where the bats can detect uh, the echo from the that bounce off from an object. So maybe by utilizing or by determining the distance, so uh, we can maximize or we can optimize our uh, the catching of bats. But with the materials actually that we are using, that's a drag for even though that's a drag for optimizing or using the echolocation of the bats against them because mist nets bounce off uh, bounce off the sound because of the arrangement of the threads. So they form
Mhm.
those
Oh.
grids, and when the sound hits that, so it generates more echo because it travels in the grid. So that's why heart traps are better at capturing uh, insectivorous bats because they transmit less echo compared to the nets because of the again the form or hmm, the arrangement of the materials in the nets.
Oh.
Uh, so, but for monitoring, if we have that uh, library for the calls, if we describe the cause of the bats in our area. So we can rely on just the bat detectors to uh, to determine what bats are active during this time or uh, what is the composition of the species in this type of environment in this microhabitat. So actually, I think for me, the goal of using bioacoustics to monitor bat species is really to lessen
Mhm.
the capturing of bats because uh, uh, being honest, capturing bats of really sometimes causes death for in some individuals, especially those to sensitive when they are captured in the net. So that's what we are trying to diminish. So the deaths caused by capturing bats.
Okay, thank you very much. Wala lang, na-curious lang ako kasi 'di ba sa birds like we employ hides, 'di ba? Camouflage para makapag-observe ka. Naisip ko lang like do we modify our garments, 'di ba? Like meron ba tayong pwedeng suotin na para you know yung bat echolocation would probably diminish para hindi tayo napapansin. Anyway,
Mm.
just a crazy idea, no? And sige, we have just one last question. I'll be combining the question of Philip and Gilbert Behek, and basically they're the same. And the last question is: can software do automated analysis and identification?
Okay, so uh, there are softwares that can do automated analysis, but this depends on the information that you input as in the program. So you still need to uh, input the description of or the data from the reference calls that you have. So still you're still dependent on a call library with this function or automated analysis. Uh, automated identification or automated analysis of uh, bat calls is available for Kaleidoscope and Analog W. But as I've said, this is dependent on what you input in the program. So you still need to include the data from your reference calls for the software to be able to identify automatically or assign an identity to the recordings that you have.
All right. Thank you very much, Kirk. And again, congratulations for that presentation and for being with us in this seminar. So, okay, and to all our participants, thank you for your questions. So we will be wrapping up our program. Let me just share my screen. Let us present this certificate of recognition to our speaker. And it reads Museum of Natural History, Office of the Vice Chancellor for Research and Extension here at UPLB College Laguna. Awards this certificate of recognition to Kirk J. Taray for serving as a resource person during this biodiversity seminar, What Does the Bat Say? An Introduction to Bat Echolocation and Bat Bioacoustics Research in the Philippines, held today, August 4, from 10 to 11:30, actually 12 noon PST, via Zoom, and in witness whereof the signature of our director is here unto affixed, and signed by Dr. Marian P. De Leon. So congratulations, Kirk. Thank you very much. And thank you for being an inspiration to our young generation of bat ecologists. And I hope maraming ma-interested sa inyo sa field na ito. Don't forget to like, follow, subscribe to our social media accounts. It's at Facebook. We have an account at Twitter, YouTube, and Instagram. Just look for the handle UPLB Museum. You could write us at mnh.uplb@up.edu.ph and visit our website, mnh.uplb.edu.ph. Check out our articles at Wikipedia and TripAdvisor. Uh, Type there UPLB Museum of Natural History. On Wednesday next week, we will have our 7th MNH Quincentennial Commemoration webinar. It's, I forgot the title, but it's for our botany group. Please visit our Facebook. Probably tomorrow we will be posting the registration details on how to uh, participate on that seminar. So maraming salamat po sa inyo lahat. Kirk, once again, thank you very much. And to all our audiences, have a great day and happy lunch.
Thank you, everyone. I hope you've picked something from my talk.
Of course. Thank you very much, Kirk. Salamat.